All right, we have remotely from Utah, so Dr. Benjamin Bikman, PhD. Dr. Bikman earned his PhD in bioenergetics at East Carolina University. His focus was on the adaptations to metabolic surgeries in obesity. We have a bariatric surgeon in the audience. As a postdoctoral fellow with the Duke National University of Singapore Medical School, Dr. Bikman continued to explore metabolic disorders with a particular focus on insulin resistance. He has continued to study insulin, including its role as a regulator of human metabolism, as well as insulin's relevance in chronic disease, as a professor at Brigham Young University and the director of its diabetes research lab. In addition to his research and teaching at BYU, Dr. Bikman serves as a research mentor, undergraduate and graduate students, and he and his students frequently present and publish their findings. He's the author of the recently published 2020 book, Why We Get Sick. I advise everybody to get this book. Please allow me to welcome our special guest live from Utah, Dr. Benjamin Bikman. All right, Ben. So we had a whole day today talking about different topics, and I know that you are the insulin man of the entire world. You've studied insulin more than anybody probably. And I thought we could start from the fundamentals of the glucose insulin feedback mechanism. What we have here, can we display the picture? What we have here, and this is from Dr. Ferranini's studies that I learned from him, is the beta cells, and in the normal circumstances, they secrete just, quote, how much insulin is needed, quote, closed, and in appropriate time course. This also, by secreting that appropriate amount of insulin, this also suppresses alpha cells activation to produce glucagon. The way I call glucagon, Dr. Ben, I call it glucagon, the glucose is gone. This is how I remember that. The combination of these two results in stimulation of uptake of glucose by muscles, adipose tissues, and a few other organs, and inhibition of endogenous glucose production, mostly by the liver, but possibly also by the kidney, as well as suppression of lipolysis and liberation of free fatty acids from triglycerides that are stored in adipose tissues. By doing that, fasting and postprandial glucose levels remain under normal control, normal limits. The dose response for stimulation of glucose uptake or suppression of endogenous production or lipolysis are very different. It takes much less insulin to suppress production than to stimulate uptake of glucose by tissues, and this is not without consequences. So under these normal circumstances, and as long as the prehepatic insulin to glucagon ratio is low, we are metabolically flexible. This means we can switch fuels, glucose in the fat state and the free fatty acid in the fasting state. This is what we call metabolic flexibility, or what we used to call it substrate competition. So the argument here, and there's no argument, the discussion here, we've had multiple speakers. Some suggested fasting, some suggested protein sparing. I suggested ketogenic diet, and you know what we do in a low-carb society. In your own research, in your own published papers and books, can you explain this phenomenon of metabolic flexibility, and what is your recommendation for our audience today?
Yes, thanks, Yosef. In fact, I compliment the writer of what you just read. That was very articulate, And I, as you put this image up here, I appreciate the time and attention that's gone into it. I know it can be a challenge to succinctly create an image to convey an idea. So my compliments to the creator here. Yeah, my view, metabolic flexibility was a term I first became familiar with almost 20 years ago. I believe the lab that first coined the term was Brett Goodpaster's lab at University of Pittsburgh, although someone there may be able to correct me. But they first coined that term, to my knowledge, to describe the phenomenon whereby people with in a healthy state, as has been noted, the human body is capable of shifting between fuels, where in a fed state, and the two primary fuels, as you described them, and I agree with that, the two primary metabolic fuels in the metabolic hybrid engine of the body is glucose or sugar, blood sugar, or fatty acids, or just fat, because of course triglycerides count too. So we'll just say fats or sugars are what the body's burning at any moment. And insulin is the dictator. It controls the metabolic switch. Now, I sometimes want to be cautious, and I don't want people to think I'm speaking too boldly or with an artificial sense of authority, but insulin is indeed the mediator or determinant, where if insulin is elevated, the body has no choice and it shifts to sugar burning primarily. If insulin is low, and that represents the fed state, which is why George Cahill, the famous fasting physiologist of decades ago, a generation ago, or a couple generations, he referred to insulin as the hormone of the fed state for that reason. When insulin is up, the body's in sugar burning mode. That is the fed state. When insulin is down, now sugar burning starts to diminish and fat burning becomes the primary source of energy for the body. So that was the idea of metabolic flexibility. You eat, and assuming there's starches and sugars in that, then the body's in sugar burning. You fast, which is to say several hours after eating, insulin has come down, the body has shifted to fat burning. Now, that was the term that Brett Goodpaster and lab referred to as metabolic flexibility. They had become more interested in the metabolic inflexibility, which is the fact that you would have the person in a fed state, they've consumed a mixed macronutrient meal, and the body is demonstrably in a glucose burning state. And we can measure this through indirect calorimetry when you have the person hooked up to a breathing apparatus, and you're just measuring the exchange of oxygen and CO2. So again, though, they confirmed the body was in sugar burning mode. However, when they would enter what should be a fasted state, that is to say several hours after eating, it was rigid, where as much as the healthy individual shifted from sugar burning to fat burning, the metabolically unhealthy individual couldn't quite get it. The gears were stuck in this metabolic engine, and the body was staying in a much more heavily sugar burning state when it should have been transitioning into fat burning. But of course, as I I explicitly mentioned, insulin is what dictates that conversion, that switch. And sure enough, insulin was staying elevated in these people. And so to kind of bring this maybe into my wheelhouse, but not artificially, I hope, what they found was that the people with insulin resistance, which is defined by a state of hyperinsulinemia, I don't want to take this onto a tangent, but there is no such thing as insulin resistance without hyperinsulinemia. And that is very important, and it helps us know when the term insulin resistance has been invoked improperly, like some people do in the context of a low carb or a ketogenic diet. They will say, well, that's a state of physiological insulin resistance. That I disagree with that sentiment completely, and I can certainly talk on that more later, because that was the tangent, and I'll get back to my answer as Joseph teed it up. So basically, the problem then with metabolic inflexibility is that insulin isn't moving like it's supposed to. In other words, it's not coming down in a fasted state. It's staying higher. And there is a threshold, albeit poorly defined. You couldn't really define it. But generally, and this is a little bit of, please everyone know, this is a little bit of my speculation mingled with some science. If insulin levels are around the teens, around 15 microunits per mil-ish, that typically represents a point at which there would be very little fat lipolysis, very little beta oxidation, and thus virtually no ketogenesis. But below that, again, depending on the person, that's when the metabolic engine can start to shift over. So around 15 microunits per mil, the body's going to have a very hard time switching from sugar burning to fat burning. And then as the fast persists, or the fasted state persists, if you will, and then the insulin comes down below 15 to 10, et cetera. Now the transition can start to occur much more obviously. And that's certainly when you would detect the transition with the respiratory exchange ratio through the indirect calorimetry that I mentioned, the technique that you can use to actually determine the metabolic fuel shift. But to kind of wrap up this rambling, long-winded answer, but to do it precisely, metabolic flexibility is a state where the body can transition quickly from sugar burning to fat burning, or transition readily, I should say, not quickly. It can readily transition from one state to the other because insulin moves well. And that is reflective of a body that is insulin sensitive. That means two things. It means insulin is working well at all of the cells across the body, and two, insulin levels are generally low in a fasted state. In contrast, if a body is insulin resistant, it will have a difficult time. It will not be metabolically flexible. What was sugar burning in a fed state kind of stays sugar burning even when it's technically, or should be, a fasted state. And that is itself a reflection of an insulin resistant body, which is a twofold issue. Just like insulin sensitivity was a twofold item, the twofold issue of insulin resistance is, one, insulin isn't working well at some cells of the body, not all, but some cells. It is not a universal phenomenon in the body that insulin just isn't working well. No, at some cells of the body, insulin isn't working well. And then second, hyperinsulinemia. There is no such thing as insulin resistance without hyperinsulinemia. Again, be it pathological or physiological. Joseph, that's the end of that answer. How's that? Any follow-up from that?
That is a perfect answer. I gave a talk on hyperinsulinemia myself today, and I referred to some of your studies as far as insulin resistance starting at the fat cell, leading to insulin resistance in the other organs. And one thing I learned from you is the defense mechanism that the fat cells have versus the pathological mechanisms at the other organs. So in your studies, you found that hypertrophic fat cells, their defense mechanism is to leak out fat out of the fat cells. And those fats that are leaked out are very toxic. Can you elaborate a little bit on this subject, please?
Yes, I'd be happy to. It's important to note, if this image is still what you guys are seeing too, basically what happens, you'll see this red arrow. In fact, Joseph, can you see you can't see my arrow on it. You see the red arrow coming from insulin up to the fat cells, the little circles in the top right corner, where you have lipolysis engaging. Is everyone seeing the same? Yep, that's what I'm talking about. Perfect. Yep, just where that arrow's going. Yep, so that arrow there is a normal response to insulin. But so I want to preface that answer by saying lipolysis itself is not inherently pathogenic. Lipolysis itself is a normal process whereby the triglycerides stored in the adipocytes are simply being pulled off one by one and then turning into free fatty acids in the plasma to be burned by the body for energy. But that should only be happening when insulin is low. And that's what starts to go wrong. When insulin is low, as the fat cell is undergoing lipolysis, all of those free fatty acids are burned throughout the body. Because if insulin is low, the burning of the fat, which is not the same as lipolysis, I'm sure that this audience is sufficiently familiar with this that I don't need to kind of go remedial or too elementary here, but this is not fat burning. That lipolysis in the top right corner is not fat burning. You should not use the word fat burning. That should be breaking down the fat. And then it's where those free fatty acids go. That's where the fat burning occurs, the actual beta oxidation and the oxidative phosphorylation of the subsequent steps of actually breaking the fat down into its waste products all the way. So that's the burning part. So again, when insulin is low, that red arrow from insulin to the fat cell is gone. And now the fat cell can undergo lipolysis very, very readily, and all those free fatty acids are being burned for energy. But again, that should only happen. Lipolysis is only happening when insulin is low, except, as Josef alluded to, when the fat cell has undergone such dramatic hypertrophy that it cannot grow anymore. Now let me just elaborate on that point for a moment. Insulin stimulates dramatic hypertrophy of fat cells. Now, even one more step back, perhaps, the fat mass on the body can grow through two different mechanisms. On one hand, you can have a person who's gaining fat primarily through hyperplasia, and that is generally a genetic phenomenon, where some people simply have the genetics to allow their fat cells to continue to multiply or proliferate or undergo hyperplasia. All of those are the same word, basically. But in that scenario, the fat cells are very modest sized. They're all very modest sized, which means they're very metabolically healthy. And they can continue to store, they get a little more fat stored in them. And the moment they start to get a little bigger, a new fat cell comes in and differentiates, and it starts to store some of the fat as well. Insulin generally will put more pressure on hypertrophy, where the fat cell number is set, but each size of the fat cell is significantly larger. This is known to happen. It was best confirmed that happens in insulin-treated diabetics, where at the site of the insulin injection, where that insulin syringe is poking into the fat cell, those fat cells are 10 times larger in volume than fat cells just a few inches away from that same site of insulin injection. And as the fat cell, now to bring it back to my actual answer, all of that was just a tangent. When the fat cell hypertrophies to this roughly 10 times volumetric size, it is literally reaching its point of maximum dimension. And I don't use the term literally too liberally. I mean, it's reaching a point beyond which it cannot grow anymore. Its membrane will start to kind of fall in on itself as it's, again, reached this 10 times volume size increase. At that point, even if insulin is continuing to elevate, now coming back to this figure, you'll see that red line from insulin to the fat cell inhibiting lipolysis. Insulin has been inhibiting fat breakdown on this fat cell, forcing it to get bigger and bigger and bigger, because fats keep coming in and insulin is not letting any fat come out. As the fat cell has hypertrophied so significantly now, fat continues to come in, but now the fat cell is telling insulin, you're trying to prevent me from leaking fat out. I can no longer allow you to do that because I have reached a point of maximum dimension, maximum volume. So even though insulin is still high, preventing the body from burning fat, I'm going to start leaking fat anyway. And basically, if I'm Ben continuing to talk on behalf of the fat cell is basically telling the rest of the body, hey, rest of the body, I'm sorry, I can't keep storing this fat anymore, even though insulin's not going to allow you to burn it because it's elevated, and if insulin's elevated, no cell can burn fat. It is impossible. And so the rest of these cells throughout the body are the innocent bystanders. And even the hypertrophic fat cell is itself a victim of this metabolic mayhem. It is basically telling insulin and the rest of the body, if I continue to grow, I'm literally going to burst apart, and that will be catastrophic. We'll have all this inflammation and this messy cleanup and maybe some necrosis. And so rather than just blow up, I'm going to start leaking these fats. And because insulin is still elevated, the rest of the body won't be able to burn the fat. So you're all going to have to store fat, even though you would rather burn it. And so all of these cells throughout the body that are poorly designed to continue to store all types of fat. It's not just triglycerides, it's also these class of fats called sphingolipids, which can get formed in the midst of the increased inflammation, which is also coming from the hypertrophic fat cell. Now, all of these cells throughout the body, because they have lots of free fatty acids that they cannot burn, and they have inflammatory mediators coming from the big swollen fat cells, they start to create a type of fat called sphingolipids. And then the sphingolipids, in particular, directly disrupt insulin's action at other cells. Anyway, there's a whole lot of nuance that goes beyond this, and even some speculation as to why. But of course, as a scientist, I can never answer why. God only knows why. I can only answer how. But that's or what, and that is what's happening. But it's helpful to refer to this very figure, where if insulin is up, free fatty acids will be down, because insulin's telling the fat cells and the rest of the body it's not time to burn energy, it's time to store energy. In fact, insulin is so determined to store energy that it will suppress metabolic rate by up to 300 calories per day when it's elevated. In contrast, when insulin is low and other hormones like glucagon, for example, now can suddenly come out from underneath insulin's dictatorial thumb, they come up, they accelerate metabolic rate to the tune of around 300 calories higher than it would be if insulin were elevated. And now the fat cells are breaking down their energy, releasing free fatty acids. The liver is breaking down its stored glycogen as glucose. And because insulin is low and metabolic rate is higher, all of the cells of the body start using all of this energy very, very readily and at a higher rate than if insulin were elevated. So, Joseph, back to the original question, because I promised I didn't forget it. All of this was hopefully answering the question and providing some nuance as well. When the fat cell becomes 10 times-ish bigger than it should, it will become insulin resistant in order to prevent further growth, but thereby leaking fats throughout the body to cells that can't burn it. They have to store it. And at the same time, as the fat cell has become 10 times volumetrically the size it should, it's also become very pro-inflammatory. Even that step is a step to try to ensure its own survival. As the fat cells get so large, they get pushed very far from blood vessels. And some of these pro-inflammatory cytokines that the hypertrophic fat cell is releasing will stimulate the growth of new blood vessels. But many of them don't help the fat cell at all and just start flowing through the blood, creating a systemic increase in inflammation. And again, the combination of those two things, fats that cells can't burn because insulin's elevated, and in pro-inflammatory cytokines because of the hypoxic fat cell, result in the kind of systemic biosynthesis and accumulation of sphingolipids that disrupt the insulin signaling cascade, promoting insulin resistance throughout the body. Now, I should just mention that while I do have a fat-first focus when it comes to insulin resistance, I believe the fat cell is the first domino to fall. There are others, and I would want everyone to know, that claim that it's the liver that becomes insulin resistant first, or it's the muscle that becomes insulin resistant first. I think the truth of it is they probably are all becoming insulin resistant around the same time, and it would be impossible to tease out which one actually goes first. My view is, and I do have additional data that I won't bother citing now, that it is the fat cell, but then in short order, or in some time later, as the liver and the muscle cells, and even the alpha cell. What's beautiful about this figure here is that all three of these other relevant variables are here. Once the alpha cell becomes insulin resistant and the liver and the muscle, that is the point where what was just insulin resistance, which is a state of high insulin but normal glucose, becomes type 2 diabetes, which is further a state of elevated insulin. But now as the insulin resistance is spread to the alpha cell, the liver, and the muscle, now the body cannot keep glucose in control anymore, and that's when the glucose rises. The tragedy with this paradigm is that while it hopefully seems so obvious to the crowd here, because we failed to look at insulin, we failed to detect the problem. And it's only once with conventional clinical care, not like Joseph, I know, but we so doggedly look at the glucose that we fail to miss this paradigm, when the insulin could be elevated for 10 or even 20 years before the glucose ever starts to move. This is insulin resistance. This is type 2 diabetes. But because the conventional paradigm is glucose-centric, we only start to detect the problem once the glucose starts to change. if we could shift the paradigm to an insulin-centric paradigm, well, then we can start to detect the metabolic disruption at the earliest stages. Because at the earliest stages, it'll be the insulin that moves, not the glucose.
This is wonderful. You and I are on the same line, actually, wavelength. We did not talk. Well, I agree with you that the whole thing starts at the fat cells. So, I mean, the leakage of the fat from the fat cells, plus from, I mean, we also have the non-alcoholic fatty liver disease, but it all starts with lipotoxicity. We did not cover palmitic acid with ceramide and all this stuff. So the whole thing with lipotoxicity, basically, you and me agree on that it starts the whole cascade of insulin resistance in the other part of the body. Now, another subject that I would like you to touch on before I'm going to end the conclusion that I would like you to end with, and of course I want to ask the audience for questions, is your solution to all this mess. And I know maybe you could summarize that. But before this, I like reading about your study in the lab, in the Petri dish, where you grew fat cells. And the fat cells, and you measured the metabolic rate of the white fat cells versus the brown cells, fat cells. And then when you gave them beta hydroxybutyrate, that those white fat cells, metabolic rates start changing towards brown. Can you explain that to my audience, please?
Oh, yes, I'd be happy to. In fact, let me just share the background of that study very briefly. In fact, I already have alluded to this a little bit when I mentioned to you guys that when insulin is high or low, metabolic rate in the body will go the opposite direction. And this has been played out in studies, particularly in David Ludwig's lab, but others as well, where, again, if insulin goes up, metabolic rate slows down. If insulin goes down, metabolic rate will accelerate. This is one of the ways that we can reconcile the endocrine and the caloric theories of obesity. There are two primary theories of why humans actually get fat. The traditional view, although not the oldest view, is that it is purely a balance of thermodynamics, calories in, calories out. The older view, and that is now the controversial view, is that no, it's a matter of hormones. The fact is, it's both. It is literally impossible to make fat cells grow without elevated insulin. I truly mean that. It cannot happen. In any organism, from fruit flies to humans and everything in between, there is no exception to this. If insulin isn't elevated, fat cells cannot grow. This is why you can have an untreated type 1 diabetic who's truly deficient in insulin, near zero, and they can eat 5,000 calories a day, and they're wasting away. It's not because there's thousands of calories of glucose coming out in the urine, as many people would like to believe. That does not happen. It's maybe a few hundred calories in the urine. It's because of two things. One, metabolic rate is about 20% higher than it should. And that's kind of getting me to my history of answering this question. We've known since the early 1900s that like two legends in their own field, Elliot Joslin in the field of endocrinology and Francis Benedict in the field of energy balance, together found in people with type 1 diabetes, before insulin was even discovered, that their metabolic rate was about 20% higher than it should be. And then it was later, decades later, that other tests found that when you gave the type 1 diabetic insulin, metabolic rate slowed to where you would expect it to be. So all of this went into the origins of my study that we did that covered fat cells in culture, fat tissue from animals, and fat tissue from humans, including myself. When we were first learning how to do fat biopsies, it was literally me laying on the bench in the lab with helping my students and another professor know how to pull fat from my own belly before we had IRB approval. Don't tell my institution. But it was pretty funny. I was telling them, I think you went in a little too deep. Like, oh, you went too far. It's past the lidocaine. So pull it out. It was pretty funny. But we got it. But nevertheless, as Joseph teed up this question, I've expressed some of the background. Now I'll just mention to you the data. Basically, when insulin is low and ketones are elevated, the white fat tissue, which is all of our subcutaneous fat and our visceral fat, the metabolic rate, particularly in the subcutaneous fat, which is what humans mostly have, that is most of our fat, it became much more metabolically active. And just to put this in context, we have little bits of brown fat. Now, we did not take brown fat biopsies from people. That's much more delicate. That's in this kind of thoracic cavity where we have our brown fat. In animals, it's in a different spot. But when we would test the metabolic rate between white and brown fat in animals, the brown fat has a metabolic rate that's about 10 times higher than the white fat. And that's because brown fat's job is to make heat. And not only does it have a lot more mitochondria, which is why it looks so reddish brown in color, but the mitochondria have a unique capacity for what's called uncoupling, which is basically to say they burn energy to create heat. Well, what we found in the white fat tissue, and I'll just cite the human data because that's the data we all care the most about. When the humans were in ketosis, their fat tissue, the metabolic rate of their white subcutaneous fat was about 3 times higher than it was when they were not in ketosis. And so this starts to, here was white fat, here was brown fat. We kind of pushed it up to about here. But appreciate, please, that a 3-fold increase in metabolic rate of white adipose tissue is not insignificant. White adipose tissue in general occupies or accounts for up to 10% of metabolic rate in some people. In people that are, of course, very obese or morbidly obese, it's much, much higher than that. But appreciate that if you can increase that tissue's metabolic rate by 3 times, you're talking about a potentially pretty meaningful amount of calories all of a sudden that begin to help the body just using more energy, burning more energy. And if you can correct that excess energy, you start to correct obesity and you start to correct insulin resistance as well. Now, Joseph, you had mentioned, you wanted me to mention that study, but preceding that, you'd asked the question about, well, how can you resolve insulin resistance? So unless there's any opposition, I'll just briefly answer that. Thumbs up. Okay. So there are 3 primary causes of insulin resistance. Not that there aren't more. There are additional noxious stimuli that can move the needle of insulin resistance, but for the most part, they either play a modest role or they play through one of these 3 primary roles. And when I say primary, I mean that each one of these that I'll outline in just a moment have been confirmed to cause insulin resistance independently of any other variable in all 3 commonly studied biomedical models, be it isolated cell cultures, be it rodents or humans at the pinnacle of all creation. In all 3 of these models, you can cause insulin resistance through these 3 ways. 1, inflammation. If immune pathways are turned on in cells, they become insulin resistant. Full stop. And this was a lot of my postdoctoral work, actually, was identifying some of those pathways. And then second, stress. And when I say stress, I mean the stress hormones. I tend to look at everything through the lens of endocrinology in a way, but cortisol and epinephrine, the 2 prototypical stress hormones, will cause insulin resistance in cells, rodents, and humans. And then third is hyperinsulinemia. So chronically elevated insulin itself is a driver of insulin resistance. And that's reflective of a fundamental biological principle. Whenever there's too much of something, the cells, or the body by extension, will attempt to become resistant to that something in order to maintain homeostasis. Now, with those 3 causes of insulin resistance in mind, we understand the solution. To varying degrees, the solution to insulin resistance should address these aspects as needed. The problem with the first 2, namely inflammation and stress, is that it is very difficult to, 1, appreciate the role to which they're truly contributing in the body. In other words, how much do they have to be increased in order to create the problem? But then second, how to actually bring them down. So let's say, for example, someone has C-reactive protein levels that are higher than ideal. And you would say to the person who also, has insulin resistance, confirmed through other tests, you would say, well, you need to bring your inflammation down. And they would say, well, how do I do that? And you would say, I don't really know. It's kind of hard to know what the cause of the inflammation is, because it is. And then second, let's say the patient has slightly higher than ideal levels of cortisol. And you would say, well, you have insulin resistance and I see your cortisol is high. We really need to bring down your cortisol. And they would say, well, how do I do that? And you would say, I don't really know. And now they're even more stressed than they were before. In other words, if along the panel that we have, that we say, this is the solution, the 3 solutions to insulin resistance or causes, you would have these 3 levers. The inflammation lever and the stress lever are both up or somewhere other than off. They're hard to pull down. It's very difficult to know how to pull those down. In contrast, the insulin lever, which will always be up in insulin resistance, there is no exception. So while the other two may be kind of up, maybe really up if it's like an autoimmune disease, or kind of somewhere in between, we know the insulin lever will be up. Thankfully, we know we can grab that firmly. If the patient says, how can I bring down my insulin? We can say, that's easy. Well, in principle, it's easy. But because it involves dietary changes and habit changes, that part's not so easy. But the concept is simple, which is fasting and carbohydrate restriction. Or I should say another one, which is energy restriction, which is to say a low-calorie diet. Just to address that one first, but to be fair, actually, let me rephrase that whole thing. There are two ways to lower insulin. One, it is by controlling carbohydrates and the frequency with which you're eating, or fasting. That will lower insulin very, very quickly. In fact, fasting per unit time will lower insulin more rapidly than anything else, thereby enhancing insulin sensitivity more rapidly than anything. But you can't fast forever. And I think it's very important to note that how you end a fast is far more important than how long you fast. But you can also, so lowering insulin will immediately start improving insulin sensitivity, but so too will lowering energy. In other words, lower calorie. It will absolutely help, which is why a lot of these clinical studies that have been published, when you put someone on a low-fat, low-calorie diet, because it's so much reduced in calories compared to where they were before the study ever started, it's not surprising that we see an improvement in insulin sensitivity in those people. But if the insulin sensitizing journey starts with the low-calorie approach, often they will fail, because if you just start with cutting calories without correcting insulin first, you will start to have a reduction in overall total energy available in the blood. This was some of David Ludwig's work at Harvard. And the moment energy availability in the blood starts to come down, the brain starts to sense that and stimulates hunger. And so if the insulin sensitizing journey starts with low energy, I predict more often than not it will fail, and fail very badly, because hunger will win. So if we take that step back and start the weight loss, the insulin sensitizing, which would also be a weight loss journey, with the low insulin approach, which is intermittent fasting and dietary rules that keep refined, especially refined carbohydrates at a minimum. So control carbs, prioritize protein, don't fear fat. That will help insulin come down, and you can eat, the patient can eat, or the person can eat when they're hungry. But fasting, structured fasts, that's a low insulin approach. And then as they become more insulin sensitive, they become more metabolically flexible. So they can now start to use their own fat for fuel. And now when they start to take the low energy approach later, putting less energy in, they're so used, they are so accustomed to using their own energy. After all, that's what all that fat tissue is. It's like they have a bunch of energy bars strapped to their body. With low insulin, now they can finally open those energy bars and use their own stored energy for fuel, because that's what it's there for. And that will be the best strategy, in my view, for improving insulin sensitivity.
God, what a beautiful, concise summary at the end there of what you would recommend. That was really, that three-pronged approach was great. I like how you say we need to shift the paradigm from chasing glucose to chasing insulin. But we chase glucose because we can measure glucose, right?
Yeah.
How do we don't measure insulin. So the $1 million or $1 billion goal there would be, how are you going to chase the insulin?
She missed my lecture.
Yeah. Well, yeah. So thank you very much for the question. To me, as we look historically, as I look, right? I mean, the beauty of being a scientist is you get paid to ask questions, right? I mean, it's kind of the noble idea of getting paid to be curious. It doesn't pay particularly well, but it's nonetheless, that makes it all the more noble, right? That's what we tell ourselves, at least. But I've asked myself, why not look at insulin in the context of insulin resistance? And I think that there are two reasons for this, historical and scientific. And you said we don't measure the insulin. That doesn't mean we can't, of course. So I'll start with that one. We can measure insulin, but it is absolutely much more technically challenging than measuring any nutrient. Nutrients, if something can be oxidized or enzymatically burned, if you will, we can measure any nutrient. People have continuous glucose monitors. That's how easy it is to measure glucose now. In the very, very near future, I can speak with some authority on that. There are going to be continuous ketone monitors and continuous lactate monitors. They're all coming out very, very soon. It's because once you crack the code on one of those kind of small carbon nutrients, you crack the code on all of them. It was just a matter of prioritizing the rest enough. Insulin and any hormone immediately is a significant hurdle to measuring. And so with regards to miniaturizing that, that's a decade out probably, but I'm certain we'll get there. But for now, it is just harder to measure insulin, but it's increasingly easy and it's increasingly affordable. And so whether the patient asks for it or whether the insurance just covers it or the clinician prioritizes it enough, more and more, and you guys would know this better than me, if a tube of blood is being sent to the lab to measure any other hormones, you're getting any other peptide hormone, especially if you're getting TSH or growth hormone, et cetera, well, there's no reason why that can't also be used to measure insulin. It's just a matter of, will the insurance cover it, which often it won't, and is the patient prepared to pay, out of pocket for it? And they may or may not. And it would certainly be partly the clinician's kind of duty to help or opportunity to help the patient understand the value of it. But that's the scientific hurdle, which was much more significant than it used to be, but it's still there. And then the second reason that I am so forgiving when I explain that paradigm, and I'm hopefully not condemning, it's the historical precedent, which was the very term diabetes essentially means polyuria. And it's this excessive production of urine. And the cause, like the root cause at the glomerulus and the renal tubules, is because of the hyperglycemia. And so the note that the early physicians made, it wasn't that the urine is sweet. That's not what actually, glucose isn't sweet, but they noticed that the dogs and the flies would come to it, and like honey. And that's where the mellitus term came from, the honeyed polyuria, basically, because they would come to it like honey. So it's the polyuria, which was the primary historical manifestation of the disease, that is a result of the hyperglycemia. And so historically it made sense. It's excusable that we would look at the glucose. But now that we have the capacity to measure insulin with every blood test, and we know the relevance of it, that it's the poor insulin handling that's resulting in the hyperglycemia. So there's no one who could argue that insulin problems will precede glucose problems. It becomes less excusable in my mind.
Dr. Sepulveda was not here when I gave the lecture on hyperinsulinemia, and I'm sorry, but I
shame on you.
I spoke about C-peptide and I spoke about insulin measurement, and we talked about Joseph Kraft and the dynamic measurement of insulin. So in my own opinion, C-peptide is a much more practical test to do specifically in a clinical setting. But Joseph, are they doing it? I'm doing it. And I already told the audience, you go to your doctor, check your C-peptide. C-peptide is more available in the blood than insulin. Insulin, as Dr. Benjamin knows, insulin is cleared by the liver and the half-life is pretty short. So if you want to get a measurement of insulin, you have to poke the patient every 5 minutes, 3 times, and get an average. This is cumbersome. All you have to do the Joseph Kraft test, where you give them 100 grams of sugar, and you graph the insulin, and you measure the insulin at 15, 30, 1 hour, 2 hours, 3 hours, 4, and 5. But who's going to take 100 grams of that? So we're not going to do that. We're doing a C-peptide. So I think C-peptide is the answer. I know you're busy. Your steaks are on the grill. I cannot thank you enough. Do you have one more?
Absolutely. I can't say no to a gal with a ponytail. Go.
This is an engineer.
Love it.
Well,
Love it.
Now, you just mentioned earlier that there might be a better way to end the fast, and I just wanted to know what that would be.
Don't eat garbage.
Sorry, you'd said a better way to end a fast. Is that what you said?
You had said something that maybe indicated there was a best practice in ending that.
Yeah. Thanks. Yeah, thanks for letting me follow up on that. I always have so many tangents I want to bring up that I go a little bit down, then I have to bring it back. That was certainly one of them. Yeah. So my view on looking at fasting is that the true metabolic power of a fast, beyond the emotional or even spiritual value that a fast, I don't mean to sound silly, but I'll just say kind of emotional, mental, where there truly is a benefit to just the part of us that is rational, and the ego in us can say to the body, I'm in charge and I'm going to tell us when we eat. So I think there's a deep value there. But beyond that, the metabolic value comes from lowering insulin. And so a true fast is what I call a caloric fast. Unfortunately, nowadays, especially, people will very enthusiastically jump into a fast without any plan on how they're going to end it. And they will fast for 24 hours or even longer, and then they're getting hungrier and hungrier and hungrier, and then they just binge. They just eat, they spike their insulin, because the hungrier we get, the more we start craving something that is salty and crunchy or sweet and gooey. I don't know that anyone would disagree with that. And wouldn't you know it, that's what's going to spike insulin and glucose the most. And they end up overeating. They have shame. They have this kind of doomed commitment to tell themselves, I'm going to do better tomorrow. And they do the exact same thing. So nowadays, unfortunately, fasting, in my view, often can become a kind of a glamorous version. And this is crass of me to say, but a binge purge cycle, essentially, metabolically, if you will. So nevertheless, the metabolic value of the fast is that it's lowered your insulin. That's a caloric fast. And I can't help but think, let's transition that then into what I call a nutrient fast. What if you could then eat, but you're keeping your insulin low? Moreover, you're eating what you need to eat. You're actually focusing on the essential parts of the diet. And there are such things as essential fatty acids that humans must eat to survive. Not that we're going to become deficient in them anytime soon. Through fasting, we wouldn't. Second, there are essential amino acids that a human must eat to survive. Well, as luck would have it, fats and proteins are both the two macronutrients that have little to no effect on insulin. And so here we were in the caloric fasted state with our insulin. Now we transition into the nutrient fast, which is basically focusing on fats and proteins. And then we've only increased insulin a little bit. We're maintaining autophagy. We're still burning fat at a higher than normal rate. And we're making ketones to feed the brain, which the brain uses very, very readily. That's a topic for another time. But we've basically the three rules. If my idea of when you end a fast, control carbohydrates, which is to say, another way, don't eat carbohydrates. Well, I should say be judicious. Be careful with carbohydrates that come from a bag or a box with a barcode. Those are going to be refined starches. Those are going to be very refined starches and sugars. Have you guys noticed my love of alliteration yet? So, and I just, the fun challenge for me is to sometimes try to think of these on the fly. But nevertheless, control carbohydrates, be smart with starches and sugars. And the easiest way to do that is if it's whole fruits and vegetables, especially vegetables that grow above the ground and fruits that are not the tropical fruits, pineapples, bananas, mangoes. My view on it is don't even count grams. Enjoy them. Because if those are whole fruits and vegetables that are the non kind of starchy and the less sugary of the fruits, then enjoy them. You almost can't overdo it. It'd be very hard, especially if you're eating them, not drinking them. Then that's rule number one. That's rule number one for me. Control carbohydrates. Rule number 2 and 3 go together because in nature they always do. Prioritize protein, and that's from animal sources, which by every metric humans absorb better and is nutritionally superior to any so-called plant protein that we in our hubris have made, thinking we know more about creation than Mother Nature or whatever power you want to invoke. But in nature, those proteins always come with fat. In our hubris, again, we've pulled them apart, and now we've extracted just pure proteins. That is not the way humans are meant to eat any animal. Fat always comes with protein. That's how we should get it. and not be afraid of it. So don't fear fat is the third part of this. When we eat fat with the protein, we digest the protein better because it's a little known fact that bile acids facilitate protein digestion. And at the same time, the combination is more anabolic. It is literally more muscle building to eat a little less protein but get a little more fat with it than it is to eat a big load of pure protein. Human studies have confirmed. And again, I think there's something kind of beautiful about that because this is what nature wants us to do. We know that in nature, there is literally no such thing as a protein that comes alone. It always comes with fat, no exception. And that's how we should eat it. And we shouldn't apologize for it. We shouldn't be skimming that fat from the milk. We shouldn't be eating low-fat cheese or low-fat yogurts or trimming or focusing on even low-fat meat. I think actually one of the problems with the modern human diet is our obsession with chicken meat. In 1909 till now, chicken went from being the least consumed meat. It was almost nothing to being multiples higher in our consumption than any other meat. I don't think that's not why we kept chickens ancestrally. It was for their eggs, which is a perfect balance of fat and protein with the yolk and the whites. Anyway, that was too long of an answer. I hope that answers my views on how to transition a fast. It's go from the caloric fast into a nutrient fast. Thank you, guys. Thanks so much. Joseph, thanks for arranging this.
Oh, my pleasure.